All right, so this is going to be a short talk on double hashing. It assumes you know regular hashing first. Regular hashing being linear hashing, which is generally considered a poor hashing algorithm. Hashing with chaining, the other one I showed you. Hashing with chaining, if you remember that one, not Dick Cheney, but chaining. Um, chaining means you either have like a linked list in every bucket, or you can have a binary search tree in every bucket. And then if you, it's doing the thing again. It's tablet, it's no chill. All right, and then if you have a binary tree in every bucket, then the worst case performance just degrades to that of a binary tree, which is not bad. I like hashing with chaining. We are going to do a variation, though, of linear hashing. So with linear hashing, let's make this array a little bit bigger here. With a, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 2, 3, 4, 5, 6, 7, 8, 9, 10. And so if we're doing linear hashing and we were to hash the number 15, 15 modulus 11 equals bucket 4. So we put the number 15 goes into bucket 4. And then if we were to hash in 26, 26 modulus 11 is also 4. So if we were doing linear hashing, we tried putting a 26 in here, then we have a step size of 1, and the 26 goes in here again. If we were to put in 37, 37 would try going here, nope, that's full, try going here, nope, that's full, and then 37 would go there. So it's a step size of 1 with linear hashing. With linear hashing, it was step size of 1. Double hashing is different from that. Oops, I deleted too much. Double hashing is different from that. Double hashing, the initial step is the same. And in fact, for pretty much all the hash tables, the initial step is basically always the same. You go to the bucket, you take the value, step 1 for basically every hash table is you take the value and you modulus it by the size, and that's the bucket you get. It puts the bucket on the skin, something like that. No, it gets the lotion on the skin. I don't know. I've never seen that movie, so I don't get the reference. Or gets the bucket again. Is that how it goes? Okay. Value modulus size equals bucket, and like that. So this is the same across like basically every hash table. I did not watch like scary movies when I was a kid. I watched like The Little Mermaid and things like that. It puts the lotion on its skin or gets the hose again. Okay, sorry. Yeah, sorry. I've never seen it. Okay. This is the same for all hashing. Now, what we're going to do is we're going to do something called double hashing. So with double hashing, the step size double hashing, the step size is going to be different. And the step size is not going to be 1, it's going to be the value, minimize my face, it's going to be the value modulus r plus 1. And if that seems weird to you, let me explain what r is. R is the prime number smaller than size. And for double hashing, your hash table has to be prime number in size as well. So, for example, we have here a table of size 11. 11 is a prime number in size, and so for R, we'll pick 7. 7 is the first prime number smaller than 11. We could pick 5 also. It doesn't really matter. And so let's do this. And I'll give you an example if that isn't clear what's going on here. So again, let's say I try hashing 15. So 15 goes into bucket 4. 15 modulus 11 is 4. It goes into bucket 4. It's open. We're done. It's exactly the same as linear hashing. Exactly the same as like with chaining, except with chaining it goes into a binary tree there. Yeah, it's essentially the same thing. It goes into the bucket. Now let's say we have a conflict. Let's try putting in 26. So 26 modulus size is again, is 4. And so 26 comes in here. Now, instead of a step size of 1 for linear hashing, just get linear hashing out of here. Instead of a step size of 1, our step size is going to be the value, 26, modulus r, which is 7. So it's going to be 26 modulus 7, quantity plus 1. So 7 divides into 26 3 times, the remainder of 5. So our step size is going to be 5 plus 1 is 6. So what that means is that the number 26 is going to go, instead of 1 to the right, it's going to go 6 to the right. 1, 2, 3, 4, 5, 6. And so 26 goes in here. Okay. And the reason for that is because when you have linear probing, what happens is you get a bunch of numbers that are all hitting kind of the same area, and it forms these like large islands of like collisions, and the bigger the island gets, the more collisions happen, and they all start running to the end one at a time. With double hashing, every time you hash a number to the same bucket location, because the step size that it gets is different, it's going to scatter across the hash table more widely, and you actually get better performance in like the 60 to 70% load range. Okay, so give me another number that hashes to 4, everybody. We'll do this again. Give me a number that hashes to 4, bucket 4. 16 is going to hash to 15, so I'll just do a solid and put a 16 in there. There you go. 37. So 37. 37 modulus 11 is 4, correct? 37 modulus 11 is 4. So 37 tries coming into here. Now the step size, let's compute that. The step size is going to be 37. 37 modulus 7 plus 1. What do you guys got for that? 3. That's what I got too. Good. So the step size is 3. So 37 goes 1 to the right, 2 to the right, 3 to the right, and 37 goes here. All right, give me another number. Give me another number that hashes to 4 or to 5 or to 7 or to 10. I'm just picking collisions right now. 48. Okay, that seems like the obvious next choice. So for 48, it's going to try hashing into here. 48 tries to come into here. It's full. I can just erase this part here. I don't have to redo the whole thing. So 48 modulus 7 plus 1. What do you guys got? What is 48 modulus 7? How many times is 7 divided into 48? I get 6 with a remainder of 6. 6 plus 1 is what? 7. Good. So 48 is going to have a step size of 7, so it's going to go 1 to the right, 2 to the right, 3 to the right, 4 to the right, 5 to the right, 6 to the right, and 7 to the right. So 48 is going to come into here. Clear? You want one more? We haven't had any double collisions yet, so 125. Okay, that also hashes to 4. Okay, so we're going to have 125. Come in here, 125, come into there. Get a collision. Step size is going to be 125 modulus 7, which is 7, I think. No, 6. I think it's 6 again. Is that what you guys get? 125 modulus 7 is 6. Switch to programmer mode. 125 mod 7 is 6. Good. Excellent. I have had enough coffee to do mental math. So 125 modulus 7 is 6, plus 1 is 7. So we go 1 to the right, 2 to the right, 3 to the right, 4 to the right, 5 to the right, 6 to the right, 7 to the right. Oop, collision again. So we will go another 7 to the right. 1, 2, 3, 4, 5, 6, 7. Nope, we got another collision. Let's go 7 to the right. 1, 2, 3, 4, 5, 6, 7. We got an open spot, and so 125. We'll go into here. And there you have it. So we haven't gone over deleting, but that's, if you're going to do a search for 125, what you're going to do is you're going to follow the same process. And again, as the hash table gets more and more full, the performance degrades. It degrades from order 1 to order n. And this is true for both linear hashing and for double hashing. But what's interesting, if we graph this out, we have the load here, and this is 0% full, and this is 100% full. The performance down here is going to be like order 1. Performance up here is going to be like order n. And so for linear hashing, which I'll draw in purple, it kind of looks like this, and it kind of gets bad, kind of like this. For double hashing, so this is going to be linear. For double hashing, it kind of looks like this. So it eventually hits order n also. As you get close to 100% full, it's going to be order n time, right? Because it's going to be going to the right, 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 finding an open spot. And by the way, it will find an open spot. This might seem a little weird to you, right? Like if you go to the right 7 over and over again, like are you guaranteed to hit an open spot? You know what I mean? Like if we're here, let's just pick another number, and let's just go like I don't know 4 to the right. 1, 2, 3, 4 collision. 1, 2, 3, 4 collision. 1, 2, 3, 4 collision. 1, 2, 3, 4 open spot. And in fact, as it turns out, that's why these things have to be prime numbers. There's actually some really interesting math theory that says if you have a array of size a prime number and you use a number smaller than it, it's not 0. That's why 0 it'll go into an infinite loop going to the right 0 every time. That's why we have a +1 here. But if you go to the right 3, it will eventually hit every spot in the array. If you go to the right 5, it'll eventually hit every spot in the array. If you go to the right 7, it'll find every spot in the array. It's pretty cool. If there's even a single open spot in there, if you go to the right over and over again from any number from 1 to 7, it'll find it no matter what. So it's like going to an almost full theater and trying to find an open seat by going to the right 7 times. Yeah, I mean, eventually you'll find it if you keep wrapping around enough. So the performance on it will definitely hit linear, but it has kind of like a better performance in sort of this range here. And so the standard library actually will rehash right around here. So once you get to about 90% full in the standard library, then it will double the size of the hash table. It'll go from a size 11 to size 22, then go up to the next prime number, size 23. It's a prime number. And then it will rehash all the elements in it. And then when that one gets 90% full, it'll go up to size 46, go up 1 to 47, and then rehash all the elements. And when that's full, it'll go up to 87 and rehash all the elements. Now, all that constant rehashing can actually slow you down. Modular arithmetic is fun, and we're going to be doing like 2 or 3 weeks of this in CSI 26. But there's hash, there's a hexadecimal. Good times. So if you know, and this is kind of relevant for your homework assignment due on Wednesday, if you know roughly how many elements you're going to be putting into your hash table, there is a member function called reserve right here. And so you can reserve, you can basically tell it about how many people you think are going to be hashed. And then it doesn't have to like grow and then rehash everything, then grow, and then rehash everything, then grow, and rehash everything. It actually will give you a pretty nice speed boost if you do that. And so I can show you how to do that real fast. So if you have an unordered set or an unordered map, doesn't matter. Unordered set of integers, whatever, named database. You can say database dot reserve, and you can put down like 100,000, and that's kind of like a hint to the standard library saying I'm expecting to have around 100,000 people in it, and so it's going to start the hash table off at size 100,000 ish. And if it gets full, it'll get bigger, but then it won't have to rehash at size 10 and 20 and 40 and 80 and 160 and 3. It will actually give you a noticeable speed up. And if you're going to be having roughly 1 million people in there, then you can reserve room for 1 million people. And so it's, I wouldn't go up to 1 billion. You're going to start running into like running out of RAM issues at that point. But, just reserve a big enough number that you can get maximum speed, because that's the whole point of a hash table, is to get maximum speed. And by having your hash table use more RAM than necessary, then your performance is going to be close to order 1, not close to order n. And that'll be a noticeable speed up if you Like even if you have like 1,000,000 elements, you might want to reserve 2,000,000. And then sure, your RAM allocation will go up by, I don't know, 8 megs or so. But what's 8 megs? You know, it'll if you get more speed for 8 megs of RAM, go for it. So that is our double hash lecture today. It's basically exactly the same as linear hashing, except instead of a step size of 1, you have a step size of this equation here. Whatever value you're hashing, modulus r being some prime number smaller than the size of the array, plus 1. And that's how far you go to the right each time with double hashing. And the restriction on double hashing is the array size must be a prime number in size, which is actually a lethal problem with it. And the reason why, like, for the very fastest hash tables, they don't actually use it, because they want the hash tables to be a power of 2 in size. Because you can do modulus with powers of 2 much faster than modulus of size 37 or whatever. Modulus actually turns out to be the limiting speed factor in a lot of cases. And so the very fastest hash tables that I've seen actually don't use double hashing, because they want to be able to do a quick modulus by power of 2. And you can do that by just bit masking. And that's maybe a lecture for another time. But double hashing is pretty cool. A lot of professional products use it. It's good stuff. And yeah, if you have any questions, let me know. Peace out.